Welcome to the research track. There will be 5 talks in this room this afternoon. The first one will be by Alain from the University of Brest. He will be talking about, well, software engineering and aerial model validation with smalltalk. So
I'm Alain Plantec from the University of Brest, France. I'm mainly involved in model-driven engineering, and more recently in the building of tools for model-driven engineering. I'm also involved in FAO, for which I'm a contributor. So, before I speak about the subject, I have to introduce the model-driven engineering. What is model-driven engineering? It's a software development process where the system is not directly developed by hands, but automatically generated from different kind of models. So it's basically it's a generative approach in software for the software development. As input, you have several kinds of models, and each models cover a particular kind, a particular aspects of the software. The output, the final output, is the code, or part of the code of the system under development. How are we using model-driven engineering? With the help of what we call model-driven engineering workbench. There are environments that are able to, in which we are able to modelize and to specify code generators with what we call the specification of generating rules. And from this kind of tool, we are able to form the models to generate the parts of the system that we have to complete by hand in order to build a real functional system. And in example here, my clients build from the model of the domain, which will be the main box, the mail address, etc. So the input will be the domain models written in UML form. We can speak also about data workbench when the target is not a classical application, but an application to build for the model, like modeling tools or language-oriented tools. Here, as input, you don't have a model, a classical model, but a model which describes a language. But the overall process is the same. You modelize your language, and with dedicated generator, you produce part of your tool. So this is why we speak about meta workbench, because it's a tool that is going to build another tool. All these tools are based on what's called the 4-level architecture. What is this? It's a consistent logical architecture where all the elements at each level are models. In model-driven engineering, we only manipulate models. The best way to understand this architecture is to start from the bottom with the runtime system, which is made of runtime instances. So these instances, which directly represent a real world artifact, is at the level 0. These running instances are described by a model, which are at level 1. For example, for our email client, we have to develop the model which describes what a mail is. In order to describe this model, you need a language. And this language could also be described with a model. This model is presented at level 2 of the 4-layer architecture and describe what the language is. Describe an aspect of the language. For example, you can have an UML model which describes the concept of class and attributes. And your mail model will be described conforming to this language. So the mail class will be conforming to the class, and the attributes of the mail concept will be described conforming to the attribute concept. Again, in order to describe this language, which is a meta language, you have to provide another model which describes all the concepts that are used at the level 2. So this is what we call the meta model, which describes the language that is used at the level 2. Generally, this meta language model is auto-descriptive. So you can describe the meta this model with itself. So this is why there are only four levels in this architecture. So now I would like to present also a particular kind of model. You see here, you see an instance of the running system which is encoded with XML. For model-driven engineering, this is also a model. So this is at level 1. This is curious because it is an instance. It's representative. It is a representation of an instance, so it is a model. And it is made conforming to what is described at the meta level. It can be made conforming to the instance description. It could be conform also to another concept, which could be the XML representation. This kind of model, we call this kind of model a snapshot, because it could be directly produced from a running system and represent the states. It can represent the states of the system at any moment. It could be produced typically with a serialization or serialization process, which will build this kind of representation from the instances of the target system. So, the goal of my presentation now is to show how Smalltalk can be used as a model-driven engineering environment. So, as a general purpose model-driven engineering environment, because not specialized for a particular domain. So, which benefits I want also to present, which benefits regarding the validation part of the model-driven engineering process. So now, I recall the process when you are modeling within a workbench. You have to elaborate your models, and also at the beginning you have to do some verification for your models. What are these verifications? This verification ensures that you use good practice for the modelization of your model. So you must check the modeling rule in general, the modeling rule and the functional requirements. And there is also another kind of verification that you can achieve. They are based on the environment, on the rules that you can express in your models. As an example, you can use OCL, for example, to express constraints on your models. And at this at these steps, at very early steps of modelization, you can check these rules. In some workbench are providing a way to automatically check this rule even with a set of with a snapshot of the system, with a set of instances. You can evaluate the rules, but few of them are able to do that. Now, after you have get your model, you can generate your system, the code of the system. Then you have to integrate manually the generated code, and you can produce a running system. You can run the system, and this is only when the system is running that you can do more verification and validation of the system. So, what are these validations? The validation is the objective is to answer to the question, do we get the right system? So, we do some controlled experiments in order to implement so that the system is supposed to achieve. We try to invalidate the model with test, prototype, formal checking, controlling, and we get end user feeling. And the expected result is to make the system actually use and to get user feedback. So with these feedbacks, you can come back to the drawing board and reiterate on the modeling. So, what are the problems here? The problem is the long delay between the elaboration, so in the LD workbench, and the place where you can do the validations, that is in target system. The change that you made in the source models are not immediately observable, because you have to produce your target system and then to observe your target system. With the model-driven engineering, you have normally you have a good separation of concern, because you manipulate several models, each one for one aspect of the system. For example, you can have the domain model, the main, you saw the main model, but you can have architectural models that you can mix and that you can use with your code generators. So there are a good separation of concern within the modeling workbench, but when the system is produced, this good separation of concern is lost because all is mixed. So the validation and the observation of the system is made more difficult. Because of the delay, designers tend to do multiple changes in one iteration. So the difficulty here is when we have problem, one iteration, several changes, which change has caused the problem. Another point is that because all that you manipulate in a workbench are models, code generators are models, generating rules are models, etc. All is models, but current model-driven workbench do not facilitate the checking of these models, that is, the models that are used to build the code generators. The consequence, it's mainly the validation cost, because of the delay and the difficulty. And also the maintenance cost. So it is not a small problem, because if you look at this report, you will see that billions of dollars are lost because of the lack of validation of the system. Of course, I would say that if you use smalltalk, you will get this money, but a small part of this money, and it's a lot. So what are we proposing? We are proposing to starting from this situation where you have only verification finally, which is done in the model-driven workbench. We want to go to this situation where you can do validation for real inside the model-driven workbench and have less verification to do on the target system. This is where we want to go. And the second point is to be able also to validate all the models that are used within the model-driven workbench. That is the generator, the roles, and the description of the platforms for the generating of the code. What validation means? Here is a kind of map, of mind map, and a formal map of what I mean when I speak of validation. We can have roughly two kinds of validation for behavior or for data. And for behavior, you can do prototypes in order to validate your system. You can do tests, unit tests, for example. And you can have more formal validation like proving or formal validation here of data. You can have also type checking. For the prototyping, you can have horizontal or vertical prototyping. Horizontal prototyping is you want to validate the several functionalities of your system. You need a lot of parts of the system to validate. Vertical is to validate one aspect of the software, one vertical aspect of the software. So, what can we expect to do within the workbench? We can expect to do more vertical prototypes, of course tests, more domain testing and unit testing. This is what programming environments allow. In the target system, what can we expect to do in the target system? More horizontal prototyping because we need a system. Acceptance testing because this is the final system which is used for acceptance testing. We can have the regression testing done within the target system or into the model-driven workbench. And the same for type checking. You can have type checking possibility in the workbench, and you can do it also in the target system because it is often implemented with a statically typed language. So what we could not expect to do with a general purpose workbench, of course, proving and formal validation. These are done with external tools that can be used from the workbench, but we don't expect to do this. They are very practical tools. So we don't target this kind of validation.
Sorry, what is formal validation?
Formal validation is, for example, you use PageNet to guarantees that your system is right. You use mathematical function, for example. So it's only possible for a limited kind of models, and you need external tools. Proving, you can use a proving machine with, for example, this book. Now, what do we need? We need an environment that provides a consistent way to modelize. Consistency is very important. And we need executable meta-models. We don't want to use code generating in order to build a code generator, for example. We don't want to have to use code generating in order to validate from the workbench. We want to be able to do that directly without code generation. We need modeling tools, and we need a page meta programming framework. That is a way to build prototypes, to build real prototypes, and a way to specify static types. But also, the target system can be used for the validation from the workbench. Why? Because the target system is the place where you can build realistic snapshots. You can build, if you are working on a mail system, on the target system, which is running, you will, in use, you will be able to produce a lot of mails, or instances of mail, instances of mailbox, etc., which can be used from the workbench in order to validate the system. So the target system is also an important element of the validation for the validation. So now, what about Smalltalk? With Smalltalk, we can have we can specify models we can constantly specify model with class, only class. Now, in Smalltalk, we have executable methods or models, because if we are using only class for model specification, we can use Smalltalk in order to run the models. We have modeling tools, and we have a rich programming framework. We have a network layer, we can have database layer, we can have a lot of things that can be used for the building of prototypes. Now, what must be provided? A way to specify static types, and a way to get realistic data snapshot from the target system. The first point is the static typing. What could be done is to use another language to decorate the specification of your physical class in order to indicate the static type that for your models. In our environment, we are using the Express language. Here you see an example, a simple example, and it's straightforward to understand this description is the description of an entity, a mail entity with sender, object, which are string. It's very simple. Express is a step ISO standard. It's a language of the step standard, which was defined to allow the definition of exchange components between systems. In fact, this model describes what you want to exchange. So you want for mail, you want to exchange the sender, the target, the subject, and the content. And of course, you have to indicate the string, the type of each element. We are using the textual version of the language. Even there is a graphical possibility, and it is statically styled language. Another point is that with Express you can describe rules and derive the attributes, computed attributes. So Platypus is the name of our Step Express environment, which we are developing in Faro. How are we using this language? In fact, we are using it in order to decorate the already existing Smalltalk classes. If we have a class mail, we can use an entity which is describing the mail entity, and which gives all the types of the attributes. But you can have more, you can have cardinalities, you can have association between entities. But the important thing is to understand that this specification is optional. You can first describe your models with classes, and then provide the static types with an express schema. So we call the level where we provide the static typing level, and the model with only smalltalk classes is done at the prototyping level. As an example, when you provide your express entity, the smalltalk code is decorated with additional functions. For example, here you can, from smalltalk, directly get the type description. By sending plastic plus metadata to a class, you get an instance which describes the main class. And for example, you can get all the explicit attributes that you have described in your entity. And select, for example, the one which name is sender. And if you see the results here, it will print a string in the transcript. So from smalltalk, you can get all the typing information that you provide in your entities. Now, how to get realistic snapshots. So the idea to benefit from the target system. And how we do that, but when we are producing our target system, we are also producing a component which is able to exchange the data from the component. So it is automatically integrated in the target system. And for debugging purpose, the system designer can implement just, for example, a button which at any moment can be pressed in order to produce the state of the system which is running. So this kind of snapshots are very useful because they are realistic. They can be, you can get very large snapshot of system that can be used for validation. For example, here is another express entity which describes the concept of mail address, with the local part, which is a string, the domain, which is a string, and the address, which is calculated from the local part on the domain. And there are two rules that are described here. The local part and the domain must be not empty. So now, how can we use this specification, and more specifically these rules, from smalltalk, and how can we use a snapshot? So the way we are integrating a snapshot is by building what we call a repository, which is a specific class which is automatically generated. And this repository is able to read the snapshot. And then when it reads the snapshot, all the instances which are in the snapshot are materialized. So it's a classical materialization process. Then in the repository, you have all the instances of the snapshot, and you can browse them. And for each of them, you can get the rules. You can have access to the rule name and directly perform the corresponding rule, which has been which code has been produced in the class in the mail address class. So from this entity mail address, when you accept this entity in our environment, all the parts, all the rules and the DRL attributes are also produced. So you can really compute these rules and these DRL attributes. Now, an example, an application of this system. We are working in our team on the validation of critical real-time system. A critical real-time system is a real-time system which can fail. For example, an avionics system. It can fail. You don't have the right to fail. So it is very important to to give designer ways to validate their specification. There are several ways to achieve that, and a very interesting way is to use the real-time scheduling theory. This real-time scheduling theory provides a lot of analytical methods that are called feasibility tests. Each feasibility test is able to is used to validate a real-time architecture in a given context. So for the validation of critical system, we have a tool which is called the Jira tool, which is able to has a lot of feasibility tests implemented. Now, unfortunately, the real-time scheduling theory is not really used. Why is it not really used? Because it is complex. It is very complex to not to the feasibility tests are not complex, but it is very complex to know which feasibility test you can use, because you can't use all of them at any time. It depends on the characteristic of the architecture that you are building. So the question is, if we want to help designer to validate the real-time system with feasibility test, we have to help designer to find which feasibility test for the architecture. So we want to build a tool for that, which from an architecture will be able to give the name of the feasibility test that the designer can apply to validate the architecture. How are we doing that? Other members of the team have categorized the real-time system following the way the tasks are exchanging data each other, or are synchronizing each other. And from this categorization, we have, for a categorization, we have a set of corresponding feasibility tests that can be applied. So if we can find which category an architecture meets, we can compute the set of possible feasibility tests that the designer can use. Of what a communication synchronization category is made? It is made of applicability assumptions. So we have an express model which describes the real-time architecture. So it is a meta model. An applicability assumptions is designed as a particular rule in this meta model. So here is, for example, an applicability assumptions. It is a rule, an express, which can be applied for generic tasks. In fact, it says that all the tasks must be periodic, because for a lot of systems, in order to be able to use feasibility test, the real-time architecture must be periodic. So here is a rule that ensures that in your architecture, all the periodic tasks, all the tasks will be periodic. So it is here. It is specified in Express, but if you enter that in Platypus, you will have the small talk, the components with the small talk. Now, what is the final goal is when you have from the goal is to build to add feasibility the specific tools for the categorization of the architecture inside CEDAR. That is, we want a CEDAR tool, which is our target system, to be able by itself to help the designer. But we are using Paro and Platypus in order to modelize our rules and to test them before before the generation of the tool. Because it is not obvious to find the good rules. We have a lot of rules, and we need to be able directly from the workbench to test if the rules are consistent. So, given that Cheddar has been previously generated, partly automatically generated with our system, it is able to produce snapshots that can be used from the environment. So, in order to test our rules, to build the feasibility test, we can use this snapshot in order to test. Here I can get an architecture, and from the workbench I can test if the rules are okay for this architecture. So before having to produce, to recompile, etc., the tool, we can evaluate our rules directly within our workbench. Given that you need 15 minutes in order to build Cheddar, you understand that it is interesting to be able to test our rules directly within Foundry. So now, as a conclusion, say that we are already using smalltalk as an MDA workbench with Platypus. So it improves early validation, and it allows better separation of consent for validation. Now, I can automate it. We actually use as a MDA workbench. In fact, we need more modeling tools. We only have the browser, as I said before, in order to build the model. So it will be interesting to have more end-user friendly way to specify the models. We need also example in the documentation because this is really feasible. The only finally we need to do tools to help the end user to adopt finance models and make it beautiful for the same reason. Regularly I see Eclipse. My students are using Eclipse, and I think that it's very beautiful tool, and students want to use this tool because not only because it's a good tool, but also because it's a beautiful tool. So we need a beautiful tool. So issues now. Express is a good data modeling language, but there are some inconsistencies between Express and smalltalk, especially for the specification of the dynamic part of the language for constraint, function, procedure, and expression. If you write a rule in smalltalk, you can do that with a method. But if you do that with Express and generate the code and accept the code within Pharo, you will not have exactly the same code. So this is an inconsistency that has to be resolved. We only have one-to-one relationship between meta model, the specification of the type of a meta model, and a meta model. This means that you can't have easily several type descriptions for the same model. Another problem is the causal connection. We have causal connection in smalltalk. That is, you can debug, change your classes, and continue to use your instances, but it is quite limited because when you have a snapshot and you do some change in your meta models, of course, the change that you are doing in your meta models can validate your snapshot. So we have to work on this aspect. So our future work, we want to improve the static typing. So maybe reuse the part of Express. Express is very interesting for the definition of entities, but maybe use a dedicated language for the type of expression and function possible. Another point would be to ensure the causal connection. The idea will be to use refactoring meta models in order to be able from change to get our snapshot right. That is, if we are doing change in our meta model, to continue to have the possibility to continue to use our snapshot, because it's a really a big problem. And on the technical part, we want to integrate it into rules. We have implemented it from nothing. Platypus is completely independent from Moose, but we would like to reuse the Moose implementation in order to benefit of all the tools that are usable with Moose. Thank you.
Any questions?
I have a question. Do you have some idea for that issue between the one-to-one model that way?
Yes. Because when you imagine you have a meta model and you want to express to type a certain aspect of your application. So you have the entity which describes this aspect. But imagine that you want to describe another aspect, and you can have intersection between them, but they can be completely separated. For example, imagine that for a problem you want to you have, for example, you can have two entities from the same classes with different attributes. So the goal will be to have a better separation of concepts. You understand that? So for now, it is impossible. You have to have one entity which gives you access to the other. So this is the way to do, but we would like to have several possibilities to precise, to annotate the student classes.
It would make sense to implement the Express, or at least the language point of view of Express on top of Helvetia, for example, in order to be able to use the regular browser or take advantage of using the debugger, for example, or it doesn't make sense.
It was an idea, but Express is not a programming language. It's a declarative language. So Helvetia is useful to run when you have a language that you want to run and to reuse the tool. This is not the case.
Okay.
If we want to run things, we run them with Kotlin.
Okay, yes, I see. Yes.